All right, example number 2. Find the flux of the force which is given as 0, 0, z across the outwardly oriented surface x squared plus y squared plus z squared equals a squared. Hopefully we recognize this as just being a sphere with a radius of a. And again, we want this to be an outwardly oriented surface. So if I just kind of looked at, and this is not what they're asking, but if I just kind of looked at the positive first octant of this surface, we've kind of seen this before, looks something like that. What we're looking for, again, we want everything to be positive and outwardly oriented, so we want all of these things to be coming from the sphere out, coming out this direction. All positive. All right, and because we are talking about a sphere, in this case, if this was the case, and this is not the case for this problem, but if this was the case, 0 would be less than theta, which would be less than pi halves, because we're only talking about from here to here, and then phi would be the same thing. And we are talking about spherical, so we would definitely want to use that in this case. We're talking about a whole sphere, though, so I just wanted to kind of give you the general idea that if it was just an eighth of a sphere, that's what you'd be looking at. But we do want the whole sphere. And what we know is that this is going to be some kind of a function of theta and phi. Theta and phi. So we'll write our function in terms of phi and theta. So x in terms of phi and theta, just spherical coordinates, a sine phi cosine theta. Y is a sine phi sine theta. And z is a cosine phi. All right, if I want partial with respect to phi, with respect to phi, this is going to be a cosine phi cosine theta. This will be negative a, still positive, a cosine phi sine theta, and then negative a sine phi. And then r of theta is going to be, that'll be negative a sine phi sine theta, a sine phi cosine theta, and 0. We need our normal vector, which is r of phi cross r of theta. And remember that this could be r of theta cross r of phi. We're going to have to determine that by seeing what the signs of these things are as we get this. So let's do this one first, which would be, see, r of phi cross r of theta is going to be, and I think we're going to have to actually do this one out here. Here's I, j, k. So getting rid of the I is going to give us 0 minus minus, so that's plus. So okay, so that's good. So this is the one we want. Okay, so I was doing the cross here kind of in my head here, and you're going to get the 0 from the j times the k main diagonal, and then you're going to get minus the k part, which is good. So we're going to have a squared sine squared phi cosine theta. Yeah, this is probably going to give us the outward one, so this is the one we want. Looking at the j, so we're going to get 0 So you got minus of minus minus, so we're going to get a minus, but we're going to make it a negative. So this is going to give us positive, so this is good. A squared sine squared phi sine theta. And then getting rid of the k stuff is going to give us, that's going to be kind of a messy one. Let's see. See if there's a shortcut to this. I'm just going to write it out. A squared sine phi cosine phi cosine squared theta plus a squared sine phi cosine phi sine squared theta. All right, so I probably could have taken a little bit of a shortcut there, because again, if you realize that if I factored out this from each one of those, I'll have a cosine squared plus sine squared of theta left over. So really what I'm left with there is the a squared sine phi cosine phi. All right, so what I can do is, it looks like I have in common, let's see, what do I have in common that's going to help out here? I have an a and a sine phi, a and a sine phi, a and a sine phi. I don't want to try and pull it. I can't pull a sine squared phi out because I only have one sine phi in the last one. And I want to keep an a in there with everything else. So what it looks like I can write this as is a sine phi on the outside of the vector, and then a sine phi cosine theta, a sine phi sine theta, a cosine phi. Now, why is that kind of important? Well, if you think about it, that's our original f of xyz. I'm sorry, that's our original r of theta. This is just the parameterized version of x, y, and z. All right, I got to take that and I got to dot it. This is actually really nice. So I'm going to have to dot this. I'm not going to put it all into the integral. It's too much to keep writing. But I got to dot that with my function. The function is 0, 0, z. But of course, z is a cosine phi. So if I dot this piece with that piece, that's 0. That piece with that piece, that's 0. So really all I get is this one times this one, and then I still have to multiply it by this outside piece here. So it looks like what I'm going to get by dotting this and then multiplying it by a sine phi, I'm going to get a cubed sine phi cosine phi, cosine squared phi, excuse me. Right? Yeah, cosine times cosine squared. And I'm going to have to take the integral, double integral over d of that dA. All right. Now, we are talking about an entire sphere here, so we're going to go from, phi is going to go from 0 to pi, from the top all the way to the bottom, and then, of course, theta goes all the way around 0 to 2 pi. This a cubed is a constant. It can be pulled out to the front. Again, phi goes from 0, phi goes from 0 to pi. Theta goes from 0 to 2 pi. And these things can be separated, which is nice. And this is going to actually be a relatively easy U substitution problem to do this integral. So let's go ahead and finish out the integral. So I'm going to have a cubed, the 0 to 2 pi of d theta, since there are no thetas, again, that's just going to give us 2 pi. Then I have this integral from 0 to pi, sine phi, cosine squared phi, d phi. Again, relatively easy u substitution. So u is cosine phi, du is negative sine phi, d phi. So d phi is du over negative sine phi. All right, let's go ahead and plug this stuff back in. So we're going to get, I'm going to change the bounds. This is going to go from, what's that going to be? Cosine of 0 is 1, cosine of pi is negative 1. So we're going to have sine phi u squared times du over negative sine phi. Of course, the sine phi's go away. This negative can change, we'll flip the bounds over, which is good because now they'll be in the right order. So we'll have 2 pi a cubed. Let's see, antiderivative is going to be 1/3 u cubed from negative 1 to 1. So we'll get 2 pi a cubed. Plugging in 1 gives us 1/3. Plugging in negative 1 gives us minus negative 1/3. So that's 2/3 times 2 pi a cubed. That's going to give us 4 pi a cubed over 3. Huh. That's interesting. Well, I guess that kind of makes sense. If it's an outward flux, I have to think about this for a second. If it's an outward flux, everything is going out of the circle or the sphere. What you get, if A is the radius, so if you wrote it in terms of r, what you really get is 4/3 pi r cubed, which is the volume of a sphere. So the volume, the whole volume of the inside of the sphere is pushing outwards. I guess that kind of makes sense. Never thought about it before. All right, so there you go. Let's go on to number 2. Number 3. All right, so number 3, find the flux of our force, which is given to us as yj minus zk, which, of course, is just, let's see, 0, y, and then negative z. Write it like that. Okay, where S consists of the paraboloid y equals x squared plus z squared, that's a little different, as y goes from 0 to 1, and the disk x squared plus z squared is less than or equal to 1, and y equals 1. All right, so what is all that? It's a little bit different because this thing is oriented differently for us. So it looks like this is a paraboloid. This piece right here is a paraboloid, but it opens starting at the origin, but it opens along the y-axis. So it looks like it's going to look something like this. And then it says, and the disk, y only goes from 0 to 1, x squared plus z squared equals 1, is this piece right here, where this is 1. Huh. Okay, so now we've got what looks to be, we've got some kind of a force which is coming in this direction into this thing, and we want to see what the flux is. Well, we want it to be, again, we want it to be an outward flux. So this is the interesting part. Once it comes into this, because it's got 2 of these pieces on it, which is a little bit different, the outward flux for the disk part has to be coming out this direction. The outward flux for, because it's got to be oriented outward, the outward flux for the paraboloid portion of it needs to be coming out this way. So I'm actually going to have to split this up into two different surfaces. Surface 1, we'll go with the paraboloid part of surface 1. So that'll be this part. So we can define this, again, it's the paraboloid portion. We can define this cylindrically or polar. So x is going to be r cosine theta. Here's the difference. Y is not going to be r sine theta. In this case, the z part is the r sine theta because of the way it's oriented. And y is the function of x squared plus z squared, which of course, again, r squared cosine squared plus r squared sine squared is just going to give us r squared. Okay, again, hopefully we've done that enough that that makes sense now. So we're going to need the partials, r sub r sub theta. Let's see, r sub r is going to be cosine theta, 2r sine theta. And then with respect to theta, that's going to be negative r sine theta, 0, and r cosine theta. And we will need to cross these things and hope that we get a flux in the correct direction. Now this is the paraboloid portion, so what we really want is we want the y direction flux to be negative. We definitely want to see that y, when we cross these things, the y part to be negative of some kind. So I'm thinking we're just going to go r cross r theta. If we get a y value that's positive, we have to just flip it. Do it the other way, do the cross the other way. So let's see, I, j, and k. If we get rid of the I, we're going to have 2r squared cosine theta minus 0. So 2r squared cosine theta. Now the important part, the j part, if we get rid of the j stuff, we're going to get r cosine squared plus r sine squared, which is r cosine squared plus r sine squared is just going to give you r. But remember, we have to make the middle term negative, so we have a negative r. This is good. This is what we want to see. And then I got to do the third component. Let me get rid of some of this. Oops. The z part, or the k part here, is 0 plus 2r squared sine theta. So I am pretty sure this is what we want for surface 1. That looks right because we want that flux to be outward. So we want it pushing out of the surface, which means it has to be going basically against the flow. Because all the flow, again, would be coming in to this drum like this, and it's going to be opposite directions. So that's good. All right, so let's go ahead and take the integral. Double integral over d. We have to do the dot product, which is going to be 2r squared cosine theta negative r 2r squared sine theta dotted with, so the original function was, go back up here, 0, y, and then negative z, right? So 0, y is r squared, and then negative z is going to be negative r sine theta dA. So let's see what we get when we dot this. Actually, I'm going to save writing this because we'll write the bounds in. So when we dot this, we're going to get 0, negative r cubed minus 2r cubed sine squared theta. Yeah, I think that's, yeah, that looks right. dr d theta, where my radius, let's see, the biggest radius we have from this up here looks like it's going to be 1. So we're going to go 0 to 1. And of course the surface goes all the way around, so 0 to 2 pi. All right, looks like we can factor out the r cubed, which is good because then we can separate these things. So factoring out, we can actually factor out a negative r cubed even. Let's do that. So let's factor out a negative r cubed. Oops. Integral from 0 to 1, negative r cubed dr, which would leave us with an integral from 0 to 2 pi. If I factor out the negative r cubed, it looks like we get 1 plus sine squared. Oh, forgot the 2. 1 plus 2 sine squared. D theta. All right, first part will not be difficult. That's negative 1/4 r cubed, 0 to 1. Plugging in a 1, you get negative 1/4. So that's not difficult. Looks like on the second one here, we're going to have to use a reduction formula. So 0 to 2 pi, 1 plus. So reducing the sine squared part, it's a half. Well, the half is going to get rid of the 2, so that's good. Of 1 minus cosine 2 theta. Yeah, that's right, d theta. So let's see, I can kind of take the antiderivative at the same time as combining these like terms. So 1 plus 1 is 2, so that'll be a 2 theta. Antiderivative of negative cosine is going to be negative 1/2 sine of 2 theta from 0 to 2 pi. So I'll get negative 1/4. Plugging in 2 pi is going to give me 4 pi. 2 pi for the theta and the sine part is 4 pi. Sine of 4 pi is 0. Plugging in 0 is going to give me 0, so that's done there. That's going to give me negative pi. That's surface 1, but that's good. We have a negative flux. That's what we should have. We have a negative flux. We have this red stuff, the red flux coming off of the paraboloid surface in the right direction. That is correct. That's what we need. All right, surface 2. Let's try and put this over here. I don't know if I'll be able to fit it. I'm going to try. Surface 2 is the disk. We want the entire disk, so we'll call x r cosine theta. Once again, the y is not going to be r sine theta because it's on the y-axis, so z is going to be the r sine theta. And then the y here, it's constant. It's 1. So this time we want a positive value because it's going in the positive y direction when we do our cross. So hopefully we'll get that. So r here in this case is going to be cosine theta, 0 sine theta. And r of theta is going to be negative r sine theta, 0, r cosine theta. All right, let's see what we get. I, j, k. I might have made this one backwards, but I think this is right. We'll see. So the I is going to be 0 minus 0. That's 0. Wonderful. So r cross r theta. The j part is going to be r cosine squared plus r sine squared, which of course is just r, so that's good. It's a positive r. This is looking good. And then for k, you're going to get 0. Wonderful. So this is outward. That's good. Positive r in the y direction tells me outward. All right, so our function here was 0, 1, negative r sine theta. And our normal vector, or f dot n, you're looking at these two things and you dot these. The only thing that's going to give me anything is the middle piece, which is r. Right? 0 times 0, r times 1, 0 times negative r sine theta. So we get r. That's nice. So our double integral, this one should be a little quicker. Double integral over d of r dA, which will be the double integral 0 to 2 pi, still going all the way around because it's the disk. 0 to 1, the radius, r, dr, d theta. So this can be separated quite easily. Again, the theta part is going to give me 2 pi. The r part is going to give us 1/2 r squared from 0 to 1. 2 and the 1/2 go away. Plugging in 1, I get 1. This is really interesting. You get pi. So the total flux is the sum of those two surfaces, which is 0. Kind of an interesting, I don't want to make that a sad face, more of a, like a, really? Did that just kind of happen? So what you get is a net fluid flow. Of 0. Basically, you have the same amount coming in that you do going out. Really interesting in both directions. All right, I think that's enough for this video. I'm going to come back with one more to do the last problem, and then that'll be done with that section.